Hello, thank you, good morning. It's a real pleasure to be here. My first visit to Tokyo. So we're going to talk about enterprise blockchains and databases, and what I mean by that are beyond just blockchain word itself, is we're talking about blockchains which have some kind of element of permissioning, which is different from cryptocurrency blockchains. And we're also going to talk a bit about the difference between an enterprise blockchain and a database, and some of the trade-offs between them. Because often people say, well, why use a blockchain in a permissioned environment? You can just use a database. And often that's true, but that's not always true. So our context is the following problem. We have a group of companies that interact with each other, and part of that interaction is data. So they need to exchange data with each other, they need to send data to each other, and they also have some desire to make sure that they share a view of the current state of that data. So in a naive, unplanned world, which still happens today, this image is a little bit how it looks. We have many companies sending information to each other. They're doing that in many different ways, sending it by email, sending Excel spreadsheets. Maybe some of them have an API, which other companies are using, but it's a big mess. And everyone's sending data to each other in different ways, and it can very easily reach a situation where these companies fall out of sync, where they don't have the same view of that data, and therefore they don't have the same view of the business process that that data is representing. So this is a problem that appears in many, many different industries, whether it's finance or healthcare or insurance or legal or government. How do we make sure that all of these companies have the same view of the truth when they're just sending data to each other? Well, the traditional solution to that problem is for these companies to either choose one of those companies or to form a new company which acts as an intermediary for that particular problem. So a single database sits inside that intermediary company. That database represents the canonical view of the truth, and then all of the other companies in that process, they send requests to that central intermediary to update the information and to retrieve the current state of the information. So the database sits in one place, and all of the other companies that want to make use of that database get access to it through that intermediary company. Now, it may be that these companies in that environment have their own databases to represent the process from their internal point of view, but they all agree that the truth, the absolute up-to-date representation of what's happening, sits inside this intermediary. And this solution can work. In an enterprise context, a blockchain is a new way to solve that same problem of ensuring that multiple companies have the same view of what's going on using some kind of shared database. But in this case, the database doesn't sit inside an intermediary. It sits inside every single company in that environment. So each company has a copy of that shared database, and they have a process of exchanging messages and information to make sure that the updates to that database are seen by all parties, and that all parties' databases remain synchronized with each other. So how do they do this? There's two primary mechanisms, and if you're familiar with cryptocurrency blockchains, you'll recognize these mechanisms. First of all, we have what's called a transaction. A transaction represents an individual event or an individual change to that database. A transaction will originate generally in one place in the network. It will be signed, that's what I signify here with a pen icon. It will be signed by the source of that information, and then the transaction travels to every other party in that network using a standard peer-to-peer method. So peer-to-peer means that every node in the network, each of which will be running in a separate company, connects to many other nodes. Every node listens for new information on the network, and every node sends out new information on the network as well to all of its connections, to all of its peers. So we have transactions that represent individual events on the network, originating somewhere, and then they propagate peer-to-peer through the network. In addition, we have blocks, and blocks represent groups of transactions that are being confirmed or validated together. Why do we need blocks and not just transactions? Well, there's a number of different reasons. Number one, we need to make sure that if someone comes onto the network late, or if someone misses some of the transactions, that they can catch up. Number two, we need to make sure that the network has an agreed ordering of what event these transactions took place in. So in a peer-to-peer network, there is no truth about what comes first and what comes second, because every node can see transactions in different orders. And you can gain some information from a transaction before you know its ordering, but ultimately you need to know its order in the final series of events to know exactly what that transaction means. We also need to be able to deal with possibility of transactions that conflict with each other. So what happens if there are two transactions on the network that conflict with each other? The same problem that you have, for example, in Bitcoin. Well, we need to have blocks there to make sure that that the transactions are confirmed as a batch, and any transaction in a block cannot then be conflicted with another transaction in that block or another transaction in a subsequent block. So transactions can originate anywhere on the network, and blocks, depending on what you choose, might be only originating from one point or from a number of points or from every point. And this is a design decision you can make. So this diagram shows a new way of managing a shared database between multiple companies without a central party in charge of that database. This is what an enterprise or a permissioned blockchain is. We might actually want to call these peer-to-peer databases rather than blockchains, because the blockchain is just the mechanism which enables this process to take place. For those of you who may be familiar with relational databases, calling this a blockchain is a bit like calling a relational database a B-tree, because relational databases have B-trees throughout. That's how they manage themselves internally, technically, but we don't call them that. We call them something which relates more to what they're used for rather than how they work. So maybe one day we won't call these things blockchains, we'll call them peer-to-peer databases. But the goal of the blockchain is to make sure that all of the peers in the network, all of the nodes in the network are in perfect agreement about what has happened, when those things happened, and the order in which they took place. So many, many things are written about blockchains, and many, many things are said about blockchains. And unfortunately, most of it is, in my view, not accurate. So I'm going to talk about some of the things that people say which are unique to blockchains, which in my view are not unique to blockchains, which a standard centralized database can also do. So for example, smart contracts. A smart contract is a piece of code which lives in a blockchain and which is executed by transactions that take place on that blockchain and which can update the state of that blockchain. That's a true statement. But standard centralized databases have something called stored procedures, which are very, very similar. Stored procedure is a piece of code, sits in the database, can respond to commands on that database and update the state of that database. So on their own, the idea of putting a logic in a database is not unique to blockchains. That can be done in other types of databases as well. Blockchains have a model in which data can only be added, what's called append-only data. So a blockchain is a log of events that take place, a log of transactions, and blockchains are designed so that you can only add new transactions onto the end, only new events onto the end of that log. Well, this is true. But if you wanted to use a relational or a standard centralized database in the same way, you could do so. You could just set the rules so that you can only create insert events, if we're talking SQL. And now we have a database where information can only be added to. People talk about blockchains as enabling safe exchanges of assets. That in a single transaction, you can have an exchange between one party holding one asset and another party holding another asset, and that exchange is atomic, meaning that either both parties swap the assets or everyone gets to keep what they started with. And this is true, you can do this in a blockchain, but you can also do this in a standard centralized database. We can define a transaction that represents both movements of assets. We have a property of relational databases called atomicity, which is part of the ACID acronym, which says that we make sure that our transactions either take place as a whole or do not take place at all. So again, this is not unique to blockchains. Lastly, blockchains give us a level of robustness which we call multi-master robustness. That means that unlike a standard replication scenario where transactions originate only in one place and travel to the other places which only read those transactions, we can initiate transactions anywhere in this network of nodes. And again, this is true. But multi-master robustness is also available in distributed databases, things like Cassandra, things like MongoDB. So a lot of these things that are said about blockchains, which make blockchains unique, these on their own don't make blockchains unique. What they do is, in combination with another property, they make blockchains interesting. Let's talk about how blockchains are worse than centralized databases. So, number one, a transaction that takes place on a blockchain is not immediate in the same way as it is in a centralized database. A centralized database has a property called durability, which means that as soon as a transaction is committed on that database, it's written to disk, and even if the power cord is pulled from that database server, the transaction and its data is not lost. Blockchains have a little bit of a more complicated time because transactions in blockchains need to achieve consensus. There needs to be some kind of discussion amongst the nodes in the network in which they confirm each other's transactions, they validate each other's transactions. So there is a delay between when a transaction takes place and when it is truly finalized. So there's a speed issue there. It's a bit like dictatorships versus democracies. So dictatorships are more efficient than democracies, right? They can make decisions faster, whereas blockchains are a little bit more like a democracy. There has to be some discussion that takes place before something is finalized. Some people think blockchains are a solution to the problem of scalability, that a blockchain can make our database run much faster than a centralized database. Unfortunately, this isn't the case. A transaction being processed by a blockchain creates more work than a transaction being processed by a centralized database, because it has to be checked against the sort of rules that we don't have in centralized databases. It has a signature which needs to be verified. That transaction also has to be done by multiple nodes in the network. So they're not faster and they're not more scalable. Lastly, some people think that because blockchains use cryptography, that they're somehow more secret than centralized databases, that they solve the problem of confidentiality in databases. And that's a complex issue, but it's not simply true. It's not true in a simple way, because blockchains, by their means of being distributed and having multiple nodes, they create the additional sharing of information compared to a centralized database. So if blockchains don't have all the unique properties that we talked about in the previous slide, and if blockchains are worse than databases in these ways, then why am I here? Why are you here? Should we finish the talk now and just describe them, just decide that they're not useful at all? Well, hopefully that won't be our conclusion. So the blockchains are actually a technology choice. And any application that you might think of building on a blockchain could be built on a centralized database, on a centralized system. And in the other direction, any application you might build on a centralized system could be built on a blockchain. This is a choice between two technologies. And like any technology choice, it comes with trade-offs. And having looked at hundreds of projects that have been built or proposed on our platform, my own conclusion is that the core trade-off in deciding whether to use a blockchain or a database for a particular application is the top line here: disintermediation versus confidentiality. So if you use a blockchain, the key property you gain of your application is disintermediation, is the ability to run that database and run that application without any individual party being in charge of it, without any individual party being in control of it. That is what blockchains give us, the ability to decentralize, to disintermediate an application. And in some cases, that is an absolutely valuable property. What's the key loss of using a blockchain? The key loss of using a blockchain for the participants in the network is reduced confidentiality. And I say reduced because there's many things you can do to mitigate this problem, but ultimately, every event that takes place on a blockchain leaves some kind of trace, and that trace is visible to all the participants in the network. So people are seeing more than they would see in a centralized database, where only the central party in a centralized database sees everything, and all the other participants see only exactly what that central party wants them to see. Blockchains are more talkative, they share more information. So that is the key trade-off, and we'll get back to this later on when we talk about use cases. Blockchains give you more disintermediation at the cost of reduced confidentiality between the participants. Now there's two other lesser trade-offs that come up quite frequently. On the plus side, blockchains give you multi-organizational robustness. What do I mean by this? I mean that a company that's participating in a blockchain, its backup strategy includes the copies of that data which are in all the other companies' servers, not just inside their own company. So when you start to think about a disaster recovery scenario, if a meteor hits your data center, you can start to think about the fact that you're not the only party which has a copy of your data and a copy of the transactions, and you can start to rely on the network to recover systems that go down, rather than having to rely on your own copy of everything. So all you really need to back up a blockchain node is private keys, which is a very small amount of information, maybe a few kilobytes, and that's it. Then you can, if you have a disaster, you can spin up a new node, load it up with your private keys, connect it to the network, and it will completely recover all of the information, all the events, all the transactions, all the blocks that took place from other parties in the network. And that's quite a nice feature that we have with blockchains. On the downside, as I mentioned, blockchains have slower performance. So if you look at blockchain platforms today, including our own, they tend to top out in the few thousands of transactions per second. A few thousand transactions per second is not bad, and it's suitable for many applications, but still, nonetheless, there are some applications that you cannot today run over a blockchain. For example, if you wanted to run the Nasdaq Stock Exchange, or probably the Tokyo Stock Exchange, over a blockchain, you'll find that it wouldn't be able to cope with the transaction volume. So we can actually take this trade-off and broaden it out a little bit, because there are actually three technologies that you can consider for coordinating data between companies. And the choice of which one is most suitable comes down to a trade-off. So if three companies want to interact with each other, There's three things they want. Sorry, if several companies interact with each other, there's three things that they want. Number one, they want real-time reconciliation. They want to know that they're in agreement with each other at all times as quickly as possible, that there's no way in which they can end up disagreeing about the state of a process or the state of a database. They also want confidentiality. They would like a world in which the only parties that see some information are those parties that that information directly involves. This is another thing that they would like, that people only see things that directly involve them. And they would also like disintermediation. They would also like to have all of this work without having to put anyone in charge of the process, because the moment you put someone in charge of that process, they have control, they can extract attacks from the system, and that's something that the participants don't want. So they want confidentiality, they want reconciliation, they want disintermediation, and unfortunately, like many things in life, many trade-offs in computer science, you can't have all three. You can only really have two. And depending on which of these two are most important for your application, that should lead you in the direction of the most appropriate architecture. So, if you want confidentiality, if you want reconciliation, and you don't mind having someone in the middle, you don't mind intermediation, you're not looking for disintermediation, then use a database. Choose a central party, run a database there. That will be reconciled immediately at all times because there is only a single database. And it will also be very, very confidential because that central party will not share information with anyone unless that party is meant to see that information. If you want confidentiality, but you don't want to have a central party running your system, you want disintermediation, and you're willing to give up reconciliation, you're willing to give up the idea that everyone has to have the same view of the data at all times, you can use messaging, like we showed in the first slide, where every party is sending messages to every other party on a one-to-one basis, on a point-to-point basis, and then you have these two properties that you're looking for, but you're not going to have real-time reconciliation. But if you want reconciliation, and you want disintermediation, and confidentiality of the data or of the transactions is less of a concern, then a blockchain can be a suitable architecture for your application. So, blockchains have been oversold. People often say that they're a solution to every single problem. That's not the case. Like any technology, there are situations where they're suitable, and there are situations where they're unsuitable. And if you spend time using a blockchain for something where it's not suitable, you're going to end up in a kind of dead end when you realize some of these problems come up. But nonetheless, if you're looking for reconciliation and disintermediation, and confidentiality is less of a concern, a blockchain can be the right solution for you. So just to clarify, so on a technical level, blockchains have a lot of similarities with what's called distributed databases. This is platforms like Cassandra or MongoDB. Transactions in both can originate anywhere on the network. There's a mechanism by which the nodes in the network reach synchronization and reach agreement on what happened. Generally speaking, these have what's called the eventually consistent model, where they're not consistent immediately, but they reach consistency over a matter of time, and hopefully a short amount of time. But there are differences between blockchains and distributed databases. It's important to clarify. So the underlying philosophical difference behind all these technical differences is that the nodes in a blockchain do not fully trust each other. If you have a distributed database, generally all of the nodes in that database are running in a single company, and every node completely trusts what is told by every other node. If a node tells another node to delete some data, or delete a table, or delete the whole database, the other node will do what it's told. It doesn't exercise any judgment in looking at the instructions it receives. Blockchains, because they run between multiple companies, they can't work like that. Even if we're not talking about malicious activity, but we're just talking about a bug in someone's software, we can't have one company exposed to a bug in the software of another company which deletes all of its data or corrupts all of its data. So nodes in a blockchain exercise judgment about every single thing they hear from other peers in the network. Is this a valid transaction? Is this a valid block? Does it follow the rules? Is it signed correctly? Does it conflict with anything else? As a result of that underlying philosophical difference, we have a lot of technical differences that come out. So for example, blockchains use public key cryptography everywhere. Asymmetric cryptography, where events, transactions, blocks are signed by particular parties, and then those signatures can be checked by other parties using the public key, which corresponds to the private key used for signing those transactions. And we need this because if I'm a node and I receive a message from another node, how do I know where that message actually originated? I don't necessarily trust the node that gave me a message. If it reports to me where that message originated from, it could fake that information, it could change that information. But if we use signatures throughout, that means that we always know where a message, be it a transaction or a block, where that message originates on the network. Blockchains have mechanisms for what we call consensual governance. That means that they are designed to be administrated by multiple parties. So generally speaking, a database in a single organization needs a single administrator, and what that administrator says goes. Delete a table, add a table, change a table. Blockchains have built-in design for consensual administration, where important changes to the blockchain, to the processes, cannot be done just by a single party, they can be done by multiple parties. Blockchains have a changed transaction model. Blockchains have a notion of, is this a valid or an invalid transaction? Now, if you look at the rules that you generally put inside centralized databases, there are rules you can express, there are constraints you can express. You can say, for example, this column cannot have a null value in it, or this column has to have a value between a certain range, or even if we have something called check constraints, you can say, well, if this column has this value, then that column has to have that value. So there are constraints in traditional databases, but those are constraints that say, is this state valid or not? Is this data valid or not? In a blockchain, we have a new type of constraint, which says, is this transaction valid or not? Is this transition valid or not? Is this change to the data a valid change or not a valid change? And we have rules built into blockchains that manage that validation. And again, we need that because it's shared between parties that do not fully trust each other. So just like there are rules about whether you drive on the left or on the right, so that the road can be shared, there are rules in blockchains that define what is a valid or an invalid transaction. And that's something new. Individual pieces of data in blockchains are owned. They can have an owner, and that owner is expressed using a public address, using essentially a hash of a public key that corresponds to a private key. So we have a notion in a blockchain that an individual piece of data can only be modified by a certain party, and the only way in which that party can modify that piece of data is if it signs a transaction with its private key that references the modification to that data. So we have ownership. We do not have generally ownership in a shared database, even if it's a distributed database. Blockchains have to worry about selective disclosure. If the nodes are running in different organizations, we don't necessarily want every organization to see everything that's going on. So there's a kind of read permissioning there, which is based on different people seeing different things. And lastly, more importantly, selective attention. Because blockchains, again, are running in different organizations, it may well be that not every organization is interested in everything going on in the network. Different organizations want to keep a track of different things. And again, this is something that's not a basic feature of distributed databases. So to summarize what a blockchain is, it's just a new type of database. If we take the world of databases and we split it into boxes, where each box represents a paradigm, a way of managing data, well, our first biggest box is relational databases, SQL databases, Oracle, MySQL, and so on and so forth. Then we have distributed databases, MongoDB, Cassandra. We have in-memory databases. We have search-oriented databases. We have graph databases. And now we have a new type of database, a blockchain. The purpose of this database is to enable it to be shared across multiple organizations, across boundaries of trust, safely and directly. And this is a new set of functionality. Of course, when people use the word blockchain, they disagree about what this word means, and I could give a whole talk about whether or not it's correct to use the word blockchain to refer to this type of database. But I don't think that's such an interesting subject. What's more interesting is to clarify the difference between the type of blockchain I'm talking about, the enterprise or permission blockchain, and the types of blockchains that underlie cryptocurrencies like Bitcoin, like Ethereum. Because technically speaking, they have a lot in common. And that's why they're both called a blockchain. They use a chain of blocks. So what are some of the differences? Number one, enterprise blockchains tend to be private, or at least partially private. So public cryptocurrency networks like Bitcoin or Ethereum are designed to be open to everybody, to transact on, to create contracts on, to build the blocks for. That's how they're designed, and that leads to certain design characteristics. Permissioned or enterprise blockchains are not fully open to everybody. They may be partially open for some types of activities, but they're generally not fully open. They give us a control over capacity and cost that we don't have in public cryptocurrencies. So for those of you who were in Marty's talk earlier, the CryptoKitties application became popular. As a result, transaction volume spiked, and costs spiked, and everything kind of fell apart. Well, that's fine for a cryptocurrency, which is still kind of the domain of enthusiasts, but enterprises can't really live with that kind of situation. They need to know what the capacity of the system is and what it's going to cost to transact over it. Generally speaking, the act of creating a block or mining or validating transactions is given to certain parties rather than being open to everybody as a whole. So we have a notion, we have control over who is validating the transactions in the network. A consequence of some of these properties is that generally speaking, enterprise blockchains don't have a native token, a native unit of value, which is like the fuel of the blockchain itself. So whereas public cryptocurrencies, they need to have some kind of money built into them at the lowest level. First of all, as a way to prevent spam, to prevent transaction spam. And second of all, as a way to incentivize the miners who are spending money building these blocks. Generally speaking, you don't need that in a permissioned blockchain because spam is less of an issue because we know who our participants are. And the act of building a block doesn't consume a meaningful amount of electricity. It takes about as much electricity as signing a transaction. It's meaningless. It's not anything like public blockchains. Permission blockchains have a defined governance model. We've talked about that already. And if you wanted to kind of summarize these things, you would say that permission blockchains are essentially a tool. There's nothing ideological about them. There's no new world view. There's no desire to change the nation state or anything else. This is a tool, which is another tool in the toolbox of enterprise IT as a way to solve certain problems. Does this alarm mean anything? Okay, we'll assume not. Okay, so let's talk about use cases. So the first use case that everyone talked about, and it's the first use case that we focused on, was the idea of moving money between banks, right? An interbank payment network. How would this work? We have many banks who would share a blockchain. Money would be issued onto this blockchain in a form of tokens, which are essentially just pieces of data that represent value. We could have instant notifications of transfers between the parties. It would work very, very quickly. We could reach final settlement in a matter of seconds. So if you think about how long it can take to settle a transaction in the traditional banking system, this sounds very fast. We have real-time reconciliation. Everyone knows everything going on at all times. There's no way in which multiple parties in the network, multiple banks, could disagree over a transaction that took place. And even better, the regulators could just plug into this network with a read-only access, and they could see everything taking place. So they wouldn't need to start asking lots of questions of all of the banks in this network, well, how much money do you have, of who, and where has it gone? Regulators could see everything at all times straight away. So this was kind of the original dream of permissioned blockchains, and this is the very first use case that drove our initial development of our product. And technically speaking, it's completely feasible. It's done, it's dusted, it works. You can do it on our platform, you can do it on other platforms. Endless pilots have been done on our platform to do this. There's only one problem. And the problem is that for this use case, the loss of confidentiality is really critical. Because actually, if you talk to banks, what they don't want is a situation where if Bank A does a transaction with Bank B, they don't want Bank C to know anything about that transaction. They don't want Bank C to even know it took place or to even know that something took place. So this idea that they could use a blockchain to move money around is very good in theory, but for kind of traditional mainstream finance, it completely falls down on the confidentiality use case. It's not really applicable in practice. Banks would prefer to have centralized systems running in some trusted party, even though they pay for that, and even though they depend, that creates a dependency for them on someone else, but the gain in confidentiality for them is worthwhile. So this is an example where the trade-off doesn't make sense. Let's talk about another type of use case. Here we have companies that are sharing information about customers with each other. So again, we have multiple companies on a blockchain. They're adding data to this blockchain in what we call in our product a stream, which is an append-only kind of database. Everything is signed, so every single piece of data in that stream, the origin of that piece of data is known based on transaction signatures. Everything is timestamped, and when it's timestamped, I don't just mean that the person or the entity creating that data says when it happens. I mean that all of the participants in the network agree on when that thing happened. So we have consensual timestamping. And I should be clear here, the resolution of this is maybe a few seconds at best. We're not talking about timestamping at the resolution of milliseconds. And we have tamper resistance, which means that once the data is entered into the system, it's very, very hard for it to be changed. But you may have heard the word immutability used for this property. I'm careful when I use the word immutability because if a meteor hit every single data center in every single company, well, that data would be lost. So there's no such thing as perfect immutability, but it's very difficult for that data to be changed. Now, what we can do in this case that we can't do so easily in the previous case is we can also use encryption. So we can encrypt this data so that it's only visible to certain parties. And the reason we can encrypt the data here and we can't encrypt the transactions before easily is that every piece of data in this type of blockchain is independent. It doesn't depend on a previous piece of data. Whereas if we're talking about money moving around, transactions have a dependency, right? If Bank A sends money to Bank B, and then Bank B sends that money onto Bank C, well, Bank C can't just trust the second transaction on its own. It has to see not only that the money was sent from Bank B to itself, but it needs to also see where the money came from. So that dependency between transactions creates a problem for confidentiality and a problem for encryption. But if we have individual separate pieces of data on the blockchain, which are just being used for the blockchain for timestamping and ordering and tamper resistance, then we can use encryption more freely, and that can solve a lot of our problems of confidentiality. And of course, nonetheless, for those parties that do see the data in this kind of blockchain, they end up with a single shared view of the truth, and this is what we gain. So this is an example of a use case where confidentiality can be, the problem of confidentiality can be mitigated, and what we gain is the disintermediation. is the ability for multiple companies to run a system like this without any individual company being in charge of it, being able to control transactions, being able to censor transactions, being able to reverse transactions. So let's talk in a broader sense. Confidentiality on the one hand versus disintermediation on the other hand. If we want to take a high-level view of use cases where blockchains make sense, we need to look for situations where we want disintermediation, where that's valuable, and where the loss of confidentiality between the participants in the network is something that at least we can live with. So here's some examples. Number one, processes that span multiple jurisdictions. So manufacturer in Japan ships goods through Europe for sale somewhere in the US. Right? We have a process there which has some data associated with it. Now where's the database going to sit to represent that process, the movement of the goods, the shipping, the orders, etc., etc.? Well, the problem in many cases is that the participants in the network can't agree on where that should be. Who is going to be in charge of maintaining the centralized database, the centralized view of the truth? Everyone wants it in their country, and everyone wants it under their legal system. So a blockchain gives you a convenient way here to sidestep the problem, to create something which, because it's disintermediated, because it has no central authority, all the participants in the network are essentially equal peers with each other, and it solves that kind of political or commercial problem of where the database sits. That's one example. And of course, you could only do this if the data in the database doesn't have a big problem of confidentiality. If we have a situation where confidentiality is still an issue, and you want disintermediation, then frankly, you'll probably still have to be stuck with paper. And that's what you see often today in many if you look at the supply chains of many very advanced goods, the supply chains themselves are still in many cases still managed through pieces of paper because of this desire to have all these properties that cannot be done together in a digital system. But if you can live with that reduction in confidentiality, a blockchain gives you a very nice way to solve the problem of where the database sits. Let's talk about aggregation. So if the purpose of a database is to aggregate data from multiple parties, and the purpose is that all of the parties can see that data, well then confidentiality isn't a problem because we're not trying to hide information from each other. So if you think, for example, of multiple stock exchanges trying to share feeds of transactions with each other, well, they don't have a problem of confidentiality. They may want to hide the information from the outside world, but they don't need to hide it from each other. And then, of course, the trade-off is a one-sided trade-off, which is that do we want disintermediation? Do we want this system to not be under the control of any central party? And often the answer is yes. So aggregation applications where we're just collecting data together can be very good use cases for blockchains. Let's talk about lightweight financial systems. So a lightweight financial system is a financial system where there's less regulation and the consequences of information leaking out are a little bit less. So we're talking about things like loyalty points, gift cards, credit systems, anything where we're not talking about really heavy parts of the economy, but something which is relatively light. And if it's relatively light, blockchains are suitable for a couple of reasons. Number one, we're not worried about confidentiality, as I mentioned. But number two, we don't need to set up a central party which is responsible for managing that system. And we don't need to depend on that central party. Because the moment you have a central party managing that system, you have contracts, you have costs, you have systems, you have buildings, you have all of these things, and they can create something which is very expensive. Well, if we can do without that, and we can have all the parties in the system transacting directly with each other, we can save a lot of money, but of course it has to be a situation where we're willing to have some loss of confidentiality. And we see this appearing often in these kind of lightweight financial systems, where that trade-off makes sense. Lastly, if the purpose of a blockchain, or the purpose of a database, is just to notarize or timestamp when things took place, a blockchain can be a very good way to do that, because that timestamping no longer depends on any individual party being accurate, but it can be based on the consensus of the network as a whole. So we gain that disintermediation. And the problem of confidentiality, the problem of desiring to keep the information secret from other parties, well, that can be solved through a simple mechanism called hashing. So if you want to take a PDF document and prove to the network that that document existed at a certain point in time, you don't have to put the whole document on the blockchain. You just calculate a hash or a fingerprint of that document, which can be tiny, maybe 32 bytes in size. That uniquely identifies that document, and no other document will match that hash. And all you need to put on the blockchain is that hash. You don't need to put the document as a whole. And I'll talk a little bit later about some of the things we're doing in Multichain relating to this approach. So one of the surprises we had when we started building this platform and seeing what people were doing with it is that there are cases where blockchains make sense inside an individual organization. And this was a surprise because everything I've said until now has been about how blockchains can solve the problem of managing a shared database across trust boundaries. So why do we have trust boundaries inside an individual organization? Well, actually, sometimes we do. There are cases where we do. So for example, sometimes an individual organization is not actually one company. If If you take any large company today, in many cases it's actually composed of multiple subsidiaries. Each subsidiary has its own legal issues, each subsidiary may be in a different country, each subsidiary needs to maintain control over its assets, whether they're financial, whether they're data, and therefore we might have a situation where these parts of a company actually want to transact with each other on an equal basis, and they don't want to run a database in headquarters, a centralized database in headquarters. They want to have a more equal relationship with each other, and a blockchain can be suitable in that case. Often we also have the ability to waive some of our concerns about confidentiality, because even though these are separate organizations, they tend to not be competing with each other. They tend to be working in different markets or in different geographies, so they're less sensitive about sharing information with each other. So there certainly are cases where a blockchain can make sense inside a single complex organization. In some countries, in some cases, it's an issue of corruption. So for example, we have a situation where some important government database is running something which is of value to the citizens, and if that database is sitting in a single place, in a single office, then someone can be given money under the table, and then they can make a modification to that database, and suddenly your car isn't your car, or your piece of land isn't your piece of land. So a blockchain gives you a way to create a database of that nature, where the only way to corrupt the database is to bribe 10 people in 10 different locations simultaneously. And that's much, much harder to do. And so we're seeing cases now where blockchains apply specifically for government use cases where there's a concern about tampering, a concern about corruption. Now it may be that you can still bribe somebody to make a new transaction in the database that isn't valid, but you cannot bribe someone to delete old data or to not leave a trail behind of what happened. Lastly, blockchains offer a very specific type of protection against cyber attack for cyber security. If a database system is running on a blockchain and one of the nodes in that blockchain is attacked, the attacker cannot delete data. They cannot corrupt or modify old data. It's true they can read a lot of data, but they cannot corrupt and modify old data. So if you have a data system where your primary concern is corruption or deletion of data, and you're not so concerned about the reading of data from cyber attack, then a blockchain can be a suitable architecture to build that one. Interesting to consider briefly why this is happening now. So there's a number of reasons. First of all, like everything else, computers, just getting faster and better. So blockchains have to work pretty hard to process a transaction compared to a centralized relational database. If you would have said to somebody 30 years ago, let's take a database that's processing a high transaction load and replicate it 100 times, they would just look at you like you were crazy because the cost of doing that was insane. But today, you can replicate databases very, very cheaply. Each of your nodes in your blockchain can be running on a $10 a month cloud server, and for very little money, you've got a very, very broad level of replication where each company is running a replica of the database. So the reduction in cost of all of these elements of computational cost is an important factor about why this technology is showing interest today. We're also living in a time when there's a very high level of integration between companies. Companies are often delivering goods to each other at very, very short notice, just-in-time manufacturing and so on. So this need for them to be able to share information and keep that information updated and synchronized in real time is higher. Globalization, of course, is a part of that. It's a part of that trend. And if we're honest, cryptocurrencies have also been a catalyst for this. So what happened historically is that Bitcoin shocked or surprised or worried the financial system because this looked like a competitor. So the financial system started looking into the technology underlying Bitcoin, and they kind of said, well, some parts of it are relevant for us, some parts of it aren't relevant for us. And that kind of subset of what cryptocurrencies do became called blockchain or DLT, distributed ledger technology. And then everyone realized that they were looking at some kind of new technology, although it's not actually new, but the level of awareness of it is new. And then that started spreading to other industries. So that's kind of the history of what happened, is that cryptocurrencies are a catalyst. So one of the curious things that we see today in our business is that when cryptocurrencies are being hyped and the value's going up, then just general level of interest in enterprise blockchains also goes up, even though there's no logical connection between the two things. And vice versa, when cryptocurrencies go wrong and people are losing their money on cryptocurrencies, people start to be more cautious again about enterprise blockchains. So that's kind of what we see in the market. So briefly, I want to talk about our own product. So Multichain is a platform for building enterprise blockchain applications. So if you think about where you would use something like Oracle or SQL Server in your development stack today for a centralized database, Multichain fulfills the same kind of role for a blockchain or for a distributed decentralized database. It's a low-level infrastructure which takes care of all the difficult things that blockchains have to do, and its purpose is to enable you to easily build your application on top of it. We've enjoyed very nice organic growth since launching the product in the middle of 2015. So developers seem to like our product, and they tend to spread the word to other developers. So over time, our product has grown quite a lot in usage, and we now have close to 10,000 downloads a month of the product, from all sorts of industries and places. As a startup company, we focus entirely on developing the core platform itself. We do not do projects for people, we do not build applications. So we have over 80 partnerships, 60 of which are with consulting companies who know the product well and who build on the product for the purposes of their clients. So when someone like Accenture or Cognizant or PwC get a client project to come in, and that client project requires a blockchain at its core, Multichain is one of the platforms they know how to use and they know how to build on in order to fulfill the requirements of that customer. In terms of what we're seeing in the market, there were many years when it was primarily POCs, proofs of concept, and pilot projects. But over the last 12 months, we've seen quite a few networks now roll out to live production deployment. This coincided with our own product reaching 1.0 general release. So things are moving, but things moved in this space much slower than was anticipated, and I think that's always the way with technology. But now we're seeing real blockchain projects come out, and what I'm pleased to say is the majority of them also make sense. Not all of them, but the majority of blockchain projects that we see moving into live production are using a blockchain in the right way to solve the right kind of problems, and they're getting additional value over using a centralized database for that same application. A bit about our product. So our goal with our product is to make it very, very easy to use, easy to configure, easy to deploy, easy to work with. We take care of a lot of the things that you need to do inside the system itself. So permissioning, all types of permissioning is built into Multichain. You don't have to build that yourself. The ability to have multiple assets issued, transferred, exchanged, and also a rich set of functionality around data, to add data to the blockchain and to index that data and query that data. Multichain is a single piece of software, so for those of you who install applications or platforms today, there's no Docker image, there's nothing like that. It's literally a single executable. And that's very important because if you want to be able to have multiple organizations participating in your network, you don't want to come with a long list of requirements for what they need in order to install your software. So it's literally a single executable, a single program that takes care of everything. Multichain runs pretty fast. So you've probably heard that the Bitcoin network can only handle something like 3 or 4 transactions per second, or the Ethereum network can only handle 10 or 12 transactions per second. So Multichain can handle, on a mid-range server, up to 1,000 transactions a second. So obviously we had to do a certain amount of work compared to traditional blockchain platforms or cryptocurrency blockchain platforms in order to make that possible. Very well documented, very stable. And one of the key characteristics of Multichain as a product is, although it's not a node on the Bitcoin network, it doesn't connect to the Bitcoin network, it has a very high level of compatibility with the Bitcoin technology, which means that if you're familiar with Bitcoin, you'll be able to work very easily with Multichain. The APIs are all backwards compatible with a lot of functionality built on top. The transaction and block formats are the same. The cryptography is the same. You can use software libraries written for Bitcoin with Multichain. You can use hardware security wallets built for Bitcoin with Multichain. So although we are a separate product, we plug in very, very well with that very large ecosystem of Bitcoin and Bitcoin derivatives, and that makes it easy for people to get up and running quickly with a product. There's a lot of tools and code out there which they can use. I mentioned briefly our next release, which is coming up. So Multichain 2.0 is currently in alpha. The last alpha will be coming out in the next couple of weeks, and then we'll be moving to beta shortly. Some functionality in Multichain 2.0 that you won't see in 1.0, so there's very deep support for JSON, putting JSON data inside your blockchain and combining that JSON data and querying that JSON data in various ways. The ability to upgrade parameters on a blockchain, so you might create a blockchain today which can support 100 transactions per second in terms of the limits you've set on the network, but you want to be able to change that in a few years' time if you change your mind, if your system grows. A lot of support for what we call off-chain data. So this relates to what I mentioned earlier, is where you only put a hash of the data on the blockchain, but the data itself is not in the chain. So that's fine, but then the question is, well, how do you deliver that data across the network? So Multichain 2.0 has built in a peer-to-peer delivery mechanism for data, a little bit like IPFS or BitTorrent, where the hashes that lock down the data and identify the data and timestamp the data go in the blockchain, but the data itself is only delivered across the network to those peers that want it, and it's delivered in a peer-to-peer way. So if you want a piece of data, you essentially send out a query to the network saying, give me that piece of data. Anyone in the network can return that data to you, and then you hash that data and compare it to the hash on the blockchain to check that it's valid compared to its origin. And Multichain 2.0 also has a feature called smart filters. So you've heard about smart contracts, which we mentioned earlier. Smart filters are another way to put logic on a blockchain, and the purpose of smart filters is to let you define custom rules regarding what is a valid transaction and what is a valid piece of data. And smart filters are written in JavaScript. They run in a deterministic version of the V8 JavaScript engine, which is used by Google Chrome and by Node.js, and they run very, very quickly, and they enable you to customize the rules of that blockchain in order to maintain data integrity. in order to make sure that whatever particular rules your application has, which define what is a valid or an invalid transaction, you can represent those rules and you can install them in the blockchain, and then every single node has to follow those rules and has no way around them. So thank you very much for listening. Come and find me later on. I'm in various other sessions if you have any questions for me. And I hope your exploration with blockchains goes well and you use them in the right way for the right things. Thank you.